Classifying discontinuities. So this is terminology or vocabulary when it comes to these graphs. So, and with special regards to limits. So this graph is a function of f. Dashed lines represent asymptotes. All right, so we have an asymptote here. Let's just go ahead and approach each one as we see it. Select the x values at which f has a jump discontinuity. And be careful, this one is choose all that apply. So it's real easy. Oh, this is one, and then you kind of forget about another, so kind of be careful. So it's not too bad on this one. It jumps for a discontinuity. As we look at this, is there anywhere where the graph jumps? And then we're looking at the input. So what's the input where it jumps at? We can see that right here at x equals -2, and this would be an infinite discontinuity, but they're not asking about that. A jump discontinuity only at x equals -2. Okay, let's keep looking. Careful, a lot of these have multiple answers. Same intro, and then let's look at the vocabulary of the answer. All right, select the x values that has a removable discontinuity. Removable means it has that open spot on the graph. You don't have to find an exact value. Remember, we're talking about the limit idea. So the removable just means that you have a gap at that spot. So there is 2 removable discontinuities at x equals -3 and x equals 6. So make sure you click on both of those answers. For this case, -3 and 6, removable, it just has the whole. It doesn't have to have another point. So notice this one doesn't have that value at -3, but we don't need it with special regards to limits. All right, more action going on here. Let's see, infinite discontinuity. So all you need is at least one at both sides going to infinity. At that point, it doesn't have to go to the same infinity. That's kind of the key here. So we're not just going into infinity. For these, it's focusing on what value of x. Select the x values. So as we look at here, where are the places that it goes to infinity at? Either both the same direction or alternating directions. So we got the same direction right here at x equals -6. So basically we're looking for asymptotes. And at x equals -2, they go to different infinities, but that's okay. It's still an infinite discontinuity with the vocabulary that they're using here. Oftentimes with these problems, vocabulary is dependent on the program or the textbook. So just make sure you adhere to the AP calculus definition of an infinite discontinuity, -6 and -2. Of course, 4 is a removable. Last one, and let's see if it's any different. It's a removable discontinuity. It looks like I only have one removable discontinuity at x equals -6. So let's just, there's a jump and there's a cusp. Let's see at -6 if we're okay with that. And that's all we need. So it has to have that little hole there, right? So if you're not sure or something's a little bit off, just make sure you refine yourself, look at the solutions if you need it. So it would just give you something like this. Looking at the graph, we can see that x -6 has that removable. And yes. So remember that it has to occur at the points where the two-sided limit exists, but doesn't equal the function at that point. So that's the issue here, is it actually equals 4. So you have to have that hole there. So just like I said.